Today we're going to be doing an Algebra 2 class on solving exponential equations. We're going to be looking at two types of exponential equations. The first type is where equations have the same base or that we can get them or write them as having the same base. The second type is where we have a single exponent and we have to use logarithms. So let's start with exponential equations that have the same base. If exponential equations have the same base, because the bases are equal, then the exponents must also be equal. So once we establish that the bases are the same, all we need to do is set the exponents equal to each other and solve. So in this case, we have 2x plus 3 equal to 5x. Subtracting 2x from both sides gives us 3 equal 3x, and dividing by 3 gives us x equal to 1. In our second example, it doesn't look like the two sides or the two exponents, exponential expressions, have the same base. On the left side, we have a base of 4, and on the right side, we have a base of 1/2. However, both of these terms are powers of 2. For instance, 4 is 2 to the second, and 1/2 is 2 to the negative first. So I'm going to replace the 4 with 2 to the second, and the 1/2 with 2 to the negative first. So on the left side, I get 2 squared to the x, and on the right side, instead of the 1/2, I'm going to replace it with 2 to the negative 1. So I have 2 to the negative 1 raised to the x minus 3. Now, using properties of exponents, a power to a power is multiplication. This becomes 2 to the 2x. And again, on the right side, using the power to a power as multiplying exponents, we get 2 to the negative x plus 3. Now they have the same base. So now I can set the exponents equal to each other. So 2x equals negative x plus 3. Adding x to both sides gives us 3x equals 3, and dividing by 3 gives us x equals 1. No, the solution is not always going to be x equals 1. Let's go ahead and look at another example. Number 3, again, the bases do not appear to be equal to each other, but 9 and 27 are both powers of 3. So 9 can be written as 3 squared, and 27 can be written as 3 to the third. So rewriting this equation, replacing 9 with 3 squared, we have 3 squared to the 2x. And on the right side, replacing 27 with 3 cubed, we have 3 cubed to the power of x minus 1. Applying the properties of exponents, we have 3 to the 4x equals 3 to the 3x minus 3. Now, setting these exponents equal to each other, we get 4x equals 3x minus 3. Subtracting 3x from both sides gives us x equal to negative 3. Okay, one more time. The bases don't appear to be the same, but they are powers of the same base. 100 is 10 squared. 1,000 is 10 cubed. So replacing those in the equation, on the left side we get 10 squared raised to the 7x plus 1. On the right side, replacing 1,000 with 10 cubed, we have 10 cubed to the 3x minus 2. Applying the properties of exponents, we have 10 to the power of 14x plus 2 equals 10 to the 9x minus 6. Now the bases are the same, so the exponents must be equal. So 14x plus 2 equals 9x minus 6. Subtracting 9x from both sides gives us 5x plus 2 equals negative 6. Subtracting 2 from both sides, 5x equals negative 8, and then dividing by 5, x is negative 8/5. So that's solving exponential equations when we have the same base, or we can write them as the same base. Now, going on to solving exponential equations that have a base only on one side, we can solve it by following these steps. We get the exponential part by itself, we take the logarithm of both sides of the equation, and then we solve for the variable. So here we have 2 to the 3x equals 5. The exponential expression is already all by itself, so step 1 is taken care of. Moving on to step 2, take the logarithm on both sides of the equation. Just like we can add the same thing to both sides of an equation, or multiply or divide both sides by the same value, or even square both sides of an equation, we can do the operation logarithm to both sides of an equation. So I'm going to choose to do either log base 10 or log base e, because those are the values that we can do on our calculator. So let's do log base 10 on this one. Log base 10 of 2 to the 3x equals log base 10 of 5. Let me grab my calculator because we're going to need it. Okay. Now, using the properties of logarithms, this exponent can be rewritten as 3x multiplied by log 2. So on the left, we have 3x times the log of 2 equal to the log of 5. I want to get x by itself. Both the 3 and the log 2 are multiplied to x, so I'm going to undo that multiplication by dividing both sides by 3 log 2. And we're going to enter that into our calculator. Make sure when you're entering into the calculator that you use the correct use of parentheses. So we're going to do the log of 5, don't forget to close the parenthesis, divided by, and I want to divide by this entire denominator. So that entire denominator needs to be in parentheses. So parentheses 3 log, notice it opens us another parenthesis, so we have to put the 2 in and close both sets of parentheses. And we end up with 0.77 to the nearest 100th. All right, let's do another one. This one, the exponential expression is not by itself on one side of the equation yet. It has the plus 1 with it. So we need to undo this plus 1 by subtracting 1 from both sides. So we get 3 to the x minus 4 equals 14. And now I'm going to do the log to both sides of this equation. This time let's just use the natural log. Remember, natural log is expressed as ln. It's base e. So we're going to do the natural log of 3 to the x minus 4 equals natural log 14. Again, using the properties of logarithms, we are going to take the exponent and rewrite this expression using a product. So we have x minus 4 in parentheses, it's the quantity x minus 4, multiplied by the natural log of 3 equals the natural log of 14. To continue to solve that, I can get into the parentheses by undoing this natural log of 3. So I'm going to divide both sides by the natural log of 3. So I end up with x minus 4 equals the natural log of 14 divided by the natural log of 3. Let's go ahead then and calculate that value. So pulling up our calculator, this time I'm using the natural log. The ln key is down towards the bottom on the right-hand side. So I'm going to hit natural log 14, close the parenthesis, divided by natural log of 3. And I get 2.40 to the nearest 100th. Now go ahead and finish solving this equation. I need to add 4 to both sides, so x is approximately equal to 6.40, anyway, to the nearest 100th. Okay, let's do a couple more and see how they work out. On this one, our exponential part is 5 to the x. I need to remove the subtract 6, and I also have this 2 that's multiplied by the exponential expression, so I need to get rid of that as well. So first, let's add 6 to both sides. I have 2 times 5 to the x equals 16. and then dividing by 2 on both sides, I have 5 to the x equals 8. Now I'm going to do the operation log to both sides of the equation. Let's just use log base 10. So log base 10 of 5 to the x equals log base 10 of 8. Using the properties of logarithms, taking this exponent and rewriting it as a product, x times the log of 5 equals the log of 8. Dividing both sides by the log of 5, we get x is equal to the log of 8 divided by the log of 5. And we can put that into our calculator, and when we do that, we get 1.29. Okay, one more. Notice that this one already has a base of e, so it's one of our desired bases. We're going to start this exactly the same way. We're going to get the exponential part, the e to the 0.2x by itself. So I'm going to undo the 1/3 by multiplying both sides by the reciprocal. I'm going to multiply both sides by 3 because I need to go 3 times 1/3. Those are reciprocals. These multiply to 1. So I have e to the 0.2x equals 21. And now since the base is our desired base of e, or even base 10, I can just rewrite this as a natural log. So we have a base e, so we can write that as natural log, okay, base e of 21 equals 0.2x. Just using our rule of rewriting an exponential equation as a log equation. So to finish this, all I need to do is divide both sides by 0.2. So I have natural log of 21 divided by 0.2. We're going to use our calculator for that, and we get 15.22. Okay, an example of a story problem. It says you deposit $2,000 in an account that pays 2.25% interest compounded monthly. How long will it take for your account to be worth $5,000? So we see that we have a compound interest situation because we're compounding monthly. So we need the compound interest rate formula. That formula is A equals P times the quantity 1 plus R over N raised to the power of N times T. So as we look through this, we see our starting value, our principal, our P, is $2,000. Our interest rate in decimal form is 0.0225. We're compounding monthly, so N is 12. And we want to end up with an accumulated amount of $5,000. So A is 5,000, and we want to find T. So let's put those into our equation. We have 5,000 equals 2,000 times the quantity 1 plus 0.0225 divided by 12 raised to the power of 12t. So here's the equation that we want to solve. I want to get t by itself. Well, the first thing I'm going to do is I'm going to divide both sides by the 2,000 because I need to get this exponential part by itself. So dividing both sides by 2,000 gives us 2.5 equals the quantity. And let's go ahead and do this quantity, this 1 plus 0.0225 divided by 12. We do want to avoid rounding at this stage because rounding at this stage can end up with a huge difference when we get to the end, especially since we're working with exponential growth. So small changes in our base, if we round, are going to end up with large changes in our answer. So avoid rounding. So we have 1 plus 0.0225 divided by 12. This is going to be our base, and we are going to keep all of those digits for our base. 1.001875 raised to the 12t power. Okay, so now that I have the exponential part by itself, I'm going to take the log to both sides. We can do log base 10 if we wish. So log of 2.5 equals log of 1.001875 to the power of 12t. Using the properties of logarithms, this exponent comes down in front to become multiplication. So we have 12t times the log of 1.001875 equals the log of 2.5. Dividing both sides by 12 times the log of 1.001875 gives us this expression, log 2.5 divided by the quantity 12, log 1.001875. And this is going to give us our value for t. Again, when writing it into your calculator, be careful to use the correct parentheses as we're working through this. So we're going to do log of 2.5 divided by, now see, I left off a parenthesis. Watch that carefully. Close that parenthesis after the log. Now, divide by the whole quantity. I want to divide by this entire thing. It must be in parentheses. So 12 log 1.001875. Close both parentheses. And we get an answer of 40.8 years. So t is equal to 40.8 years. It's going to take almost 41 years for $2,000 to grow to $5,000 when the interest rate is 2.25% compounded monthly. Okay, that's solving exponential equations.